Close your eyes for a second. No, seriously, just try it. I want you to erase everything you know. Erase the traffic you hear outside the room you're in. Erase the ground beneath your feet.
It's a powerful exercise.
Now go further. Erase the sky. I want you to imagine a time, well, before time itself. A time before there was an earth to stand on, before a sun to, warm your face, before there were even stars to look up at.
It's a pretty haunting image, isn't it? Just nothingness.
It's actually worse than nothingness. Imagine a universe that isn't this huge open space, but it's a single point.
Right.
Infinite density, infinite heat. A tiny, tiny ball, smaller than a singular atom, holding every single thing that ever was, is, and ever will be. It's almost claustrophobic when you think about it.
And that's what scientists call the singularity. That's the moment just before the cosmic clock really started ticking.
And usually, when we talk about this stuff, the Big Bang, swirling nebulas, the birth of stars, we think we're in an astronomy class. We think of Carl Sagan, maybe Neil deGrasse Tyson.
Sure, the popular science icons.
Exactly.
Yeah.
But today, we are doing something completely different. We are taking that massive cosmic scale and we're anchoring it right down to the bedrock of your UPSC preparation.
Because here's the fundamental truth. You really can't understand the mountains, the oceans, the atmosphere, the very ground you're tested on, if you don't first understand the, frankly, violent and chaotic history of how it all got here.
So welcome to this special deep dive. I'm your host, and this is brought to you by the Simplified UPSC by PPP YouTube channel. Our mission today is simple, but it's also incredibly ambitious. We're going to decode Chapter 2 of the Class 11 insert, The Origin and Evolution of the Earth.
And we want to be clear, we're not just reading the Chapter 2. We are deconstructing it.
We're taking those dense scientific theories from the Big Bang all the way to something called the Big Splat, and we are linking them step by step directly to UPSC Mains and Prelims questions.
We want to show you how this, what you might call static or theoretical knowledge, actually applies when you're in the exam hall.
That's the whole game, right? Transforming knowledge into marks.
That's the key.
Exactly. Now, before we launch ourselves into the cosmos, I do have a humble request. We pour a massive amount of work into synthesizing these deep dives. The goal is to save you time and hopefully boost your retention. So if you're finding value in this, please take a second and subscribe to the Simplified UPSC by PPP channel. It genuinely helps keep this content flowing.
And for those of you who are in a position to do so, we also have a Patreon. It's a way you can directly support us. It helps us keep the lights on and lets us keep bringing you the super useful content.
A huge, massive shout out to all of our current supporters. You guys are, and I mean this literally, the bedrock of this channel. We appreciate you more than you know. Also, don't forget to hit like on the video, or I guess audio in this case, and please leave a valuable comment. Let us know what clicked for you.
That engagement really does help the algorithm, which in turn helps us help more learners like you.
Okay, one last resource alert before we get started. I know you guys love notes. We have free notes and practice previous year questions. We call them PYQs. Available on our public Telegram channel. But if you want to really level up,
then you need to check out the private Telegram library.
That's right. The private library is where the real work gets done. You get access to all the videos of this series at once. You get organized premium notes, detailed explanations, extra PYQs, and this is the big one model mains answers.
And those model answers are absolute gold for understanding how to structure your thoughts for the actual exam. They show you how to build an argument.
So if you want in on that, just send a DM on the Telegram public channel to join the private library. Okay, pitch over. Let's get to the science.
Let's do it.
So we're looking at NCERT Class 11, Fundamentals of Physical Geography, Chapter 2. The title is The Origin and Evolution of the Earth. And honestly, when you first open this chapter, it starts with a question that feels, well, almost impossible to answer. How did early scientists, guys without Hubble telescopes, without supercomputers, arguably, probably without decent coffee, how did they even begin to guess how the Earth was formed?
It is incredibly impressive when you think about it. It just goes to show the power of pure logic and, mathematics. In the text, we basically divide these theories into two big buckets: the early theories and the modern theories.
Okay, let's unpack those early theories first. They feel a bit more philosophical, maybe, or imaginative. Is that the right word?
In a way, yeah. But they were grounded in observation, what little they had. The big name here, the starting point for this whole discussion, is Immanuel Kant.
The German philosopher. I always associate him with ethics, the categorical imperative, not planetary formation.
The very same guy. He was a polymath. He was interested in everything. And he proposed what we now call the nebular hypothesis. Later on, in 1796, a mathematician named Laplace came along and revised it.
Okay, so what was the core concept they were working with?
The concept itself is actually quite beautiful and simple. They imagined that all the planets formed out of a huge cloud of material, a nebula, that was associated with a youthful sun.
Youthful sun. I like that phrasing. It makes it sound like the sun was just a teenager spinning around trying to figure itself out.
That's a great way to put it. It was slowly rotating. And the idea was that as it spun, material clumped together, it condensed, and that's how you got the planets. It was a very solar-centric view.
Meaning everything came from one source.
Exactly. This is often called a monistic theory, meaning, one parent, the sun and its cloud.
But then we fast forward to 1900, and things get a little more dramatic.
Yeah.
We get something called the cigar theory, which I have to say sounds like something a detective in a noir film would come up with.
Yeah.
Chamberlain and Moulton, right?
It does have that kind of ring to it, doesn't it? But the shape actually refers to the debris that was pulled off the sun, not the detective smoking it. This is what's known as the wandering star hypothesis.
So we're moving away from the idea of a lonely sun spinning in the dark.
Yes. This is a dualistic or biparental theory. Chamberlain and Moulton suggested that our sun wasn't alone. A wandering star came along and approached our sun. It just passed by.
Okay.
But because stars are so massive, they have this immense gravity. As this wandering star got close, it exerted a powerful gravitational pull on the sun's surface.
Kind of like how the moon pulls the tides on Earth.
It's a similar principle, yes, but on a massive, fiery scale. It pulled what they described as a cigar-shaped extension of material right off the solar surface. A huge plume of solar matter literally ripped away from the sun.
Wow. So the sun basically got sideswiped by a cosmic hit-and-run driver.
That's one way to look at it. So the wandering star kept on going, it moved away, but that cigar-shaped material, it didn't just snap back into the sun, it got separated.
And it was trapped in orbit.
Exactly. It started revolving around the sun, and over a long, long time, it cooled down and condensed. That, according to them, is how we got planets.
And this wasn't just some fringe idea, right? This was the mainstream science of its time.
Oh, absolutely. It had some heavy hitters backing it. Sir James Jeans and Sir Harold Jeffrey, they both supported this idea. Later on, there were even variations on it called binary theories.
What were those?
The argument there was that maybe the sun had a companion star all along, coexisting with it, and some kind of interaction between them is what caused the planets to form.
It's like a cosmic soap opera.
Yeah.
First the sun is single, then it gets sideswiped by a stranger, then maybe it had a secret partner all along.
Science often mirrors our own dramas, doesn't it? But come 1950, the pendulum swung back. You had Otto Schmidt in Russia and Carl Weizsäcker in Germany, and they looked at that old nebular hypothesis again, Kant and Laplace's idea, and they said, you know what? They were actually onto something.
The Great Revision.
Yeah.
So what did they change? Because we can't just go back to the science of 1796.
No, of course not. They added a lot more detail and, crucially, a lot more physics. They said, yes, the sun was surrounded by a solar nebula, but they specified it was mostly hydrogen and helium, plus some dust particles, what they called cosmic dust.
Okay, so a more detailed recipe.
A much more detailed recipe. And they introduced the mechanism of friction and collision. You have all these particles bumping into each other, losing energy, and starting to flatten out into a disc-shaped cloud. And most importantly, they introduced the concept of accretion.
Accretion. Okay, that's a word we need to bookmark. It comes up over and over in this chapter.
Yes, it is fundamental. Accretion is simply the process where particles stick together to form larger and larger bodies. It's like a snowball rolling downhill. So, through accretion, this disk of dust and gas slowly, methodically built up into planets. It's less explosive than the wandering star theory and much more constructive.
So we went from a cloud to a cigar and then back to a disk. It feels like we're getting closer. But then something shifted in the scientific community. You mentioned the modern theories.
That's right. And the shift wasn't just about having better telescopes or more data. It was a fundamental shift in the question itself. Scientists stopped asking, how did the Earth form? And they started asking a much bigger question.
How did the universe form?
Exactly. Because if you can figure out the origin of the whole bucket, you'll have a much better chance of understanding the drops of water inside it.
And this brings us to the big one. The theory that everyone knows, or at least thinks they know, the Big Bang.
Or, to give it its more formal name, the expanding universe hypothesis.
And the man of the hour here is Edwin Hubble, right? Back in 1920.
Correct. Hubble was the one who provided the concrete evidence. He was observing distant galaxies, and he noticed something incredible. They are all moving further and further apart from us and from each other. The universe is expanding.
Okay, let's talk about the balloon experiment for a second, because the NCERT text uses this, and I definitely remember doing this in a school science class. You take a balloon, you draw little dots on it with a marker, and you call those dots galaxies. Then you start blowing it up.
Right, and as you inflate it, what happens to the dots?
Well, they all move away from each other. The space between them literally grows, and the more you blow, the faster the ones furthest away seem to move.
It's a fantastic visualization for the concept of an expanding universe, but there's a catch, and the NCERT is very careful to point this out. Analogies in science are useful, but they always break down somewhere.
And this is where it gets really interesting for, deeper understanding. What is the flaw in the balloon analogy?
Think about the ink on the rubber of the balloon. As you inflate it, the dots themselves, the ink marks, what do?
They stretch, they get bigger.
They get bigger. The little galaxy dots would become big galaxy blobs. But in reality, when we look out into the universe, scientific observations show that the galaxies themselves are not expanding.
So the Milky Way isn't getting puffier.
Not at all. Its own internal gravity holds it together quite nicely. It is only the space between the galaxies that is expanding. So the balloon analogy is great for showing how the distances increase, but it fails on the point of the size of the galaxies themselves.
That is a really crucial distinction. It's not an explosion in space. It's an expansion of space itself.
You've nailed it. That's the core concept.
Okay, let's run the timeline of this expansion. Because the Big Bang isn't just a single moment of explosion, it's a sequence of events. We have to start with that singularity we visualized at the beginning.
The tiny ball, as the text calls it. You have to try and imagine everything in the known universe. All matter, all energy, all space and time compressed into a singular atom. An unimaginably small volume. An infinite temperature, an infinite density.
It sounds impossible. It defies the physics we learn in school.
It defies our current understanding of physics. The laws as we know them break down at that point. But then, 13.7 billion years ago, bang!
It's explosion.
A violent, rapid expansion. And it happened incredibly fast. We're talking about fractions of a second for the universe to grow exponentially. Then the rate of expansion slowed down. And in that incredible process, energy started converting into matter.
The famous EMC1.
That's the one. Pure energy becoming the stuff we're made of.
There are two key milestones the NCERT highlights that I think are just super cool. The first is what happened in the first 3 minutes.
Yes, it's staggering. Within just the first 3 minutes of the Big Bang, the very first atom begins to form.
3 minutes. It takes me longer than that to boil an egg in the morning.
It's humbling, isn't it? The universe was already making the fundamental building blocks of reality. Then you jump forward to about 300,000 years after the Bang. This is another huge moment.
What happens then?
The temperature of the universe drops to about 4,500 Kelvin. At that point, atomic matter fully forms. And because of that, the universe becomes transparent.
Transparent? You mean it was opaque before that? Like a thick fog?
Exactly like a fog. It was so dense and so hot, this kind of plasma soup of particles, that light or photons couldn't travel freely. They would just get scattered, constantly bumping into electrons and protons.
So you couldn't see anything?
You couldn't see anything for more than a few feet. But once it cooled enough for electrons to combine with nuclei and form stable atoms, suddenly the path was clear. Light could finally travel unimpeded across the universe.
And that first light is something we can still detect today, right?
We can. It's called the cosmic microwave background radiation. It's literally the afterglow of the Big Bang. It's like the universe's baby picture.
That is mind-blowing. Now, just to be thorough, there was an alternative theory for a while, wasn't there? Hoyle.
Yes, Fred Hoyle's steady-state theory. He was actually the one who coined the term Big Bang as a bit of an insult. His theory argued that the universe, on the whole, stays roughly the same at any point in time. It doesn't have a beginning or an end. It just is.
So how did it account for the expansion?
It proposed that new matter was constantly being created to fill the gaps as galaxies moved apart. But the evidence for expansion, and especially the discovery of the cosmic microwave background, really overwhelmed the steady-state theory. The scientific community is now firmly in the Big Bang camp.
Now, I want to pause here and connect this directly to the exam, because talking about the Big Bang is fascinating, but how does the UPSC test this? I'm looking at the 2013 Civil Services Prelims, Paper 1.
Yes, the Higgs boson question.
Exactly. The question asked about the importance of discovering the Higgs boson particle. And one of the key statements to evaluate was, it will enable us to understand as to why elementary particles have mass.
This is a perfect linkage. We just talked about energy converting to matter right after the Big Bang. Well, the Higgs mechanism and the Higgs boson is the missing piece of that puzzle. It explains how that newly formed matter, those elementary particles, got their mass.
So without it, they would just be massless.
They'd just zip around at the speed of light. They would never clump together. They'd never form atoms, never form stars, never form planets, and certainly never form us. The Higgs field is what gives the universe its substance.
So when you're studying the formation of matter in the NCERT, you have to be ready to link it to modern physics concepts like the Higgs boson. That's the kind of depth the UPSC is looking for. It's not just the universe exploded, it's how did that explosion lead to mass and structure?
Exactly. It's not just ancient history, it's the fundamental physics of existence.
Okay, so moving on from the bang to the stars. Because the universe isn't just a smooth, transparent soup after 300,000 years, it's lumpy.
Lumpy is a very good scientific term for it. The distribution of matter and energy wasn't perfectly even. There were tiny, minuscule differences in density from one place to another.
And gravity loves density.
It absolutely does. Gravity is an amplifier. It takes those small differences and makes them bigger. It starts pulling matter together. So you get these localized clumps of gas, mostly hydrogen, gathering in these enormous clouds that we call nebulas.
And then inside these giant nebulas, the clumps just get denser and denser under their own gravity until
Poof.
poof is a good word for it. They get so hot and so dense that nuclear fusion ignites at their core. And that's the birth of a star. This started happening around 5 to 6 billion years ago.
So wait, the universe is 13.7 billion years old, but our star, the sun, is only about 5 or 6 billion years old.
That's right. Our sun is a relative latecomer. It's probably a second or even third generation star, formed from the remnants of older stars that lived and died before it. Now, speaking of stars, we have to talk about distance. Because space is big, like really, really big. And the NCERT makes a specific point to clarify the term light year.
This is a classic trap for students. A light year sounds like a measure of time because, it has the word year in it.
Right.
But it is strictly a measure of distance. It has nothing to do with time.
It's the distance that light can travel in 1 year.
Precisely. And light travels at an incredible 300,000 kilometers per second. So if you do the math, 1 light year works out to be about 9.461 trillion kilometers.
That's a number that's just too big to really comprehend. I prefer the light minute stat that's also in the book.
It's much more relatable, isn't it? The distance from the sun to the Earth is about 149,598,000 kilometers. In terms of light speed, that's roughly 8.3011 light minutes.
So when we look up at the sun, which you shouldn't do directly, we are seeing it as it was over 8 minutes ago.
That's right. If the sun were to magically vanish right this second, we wouldn't know about it for another 8 minutes. We'd be sitting here recording this deep dive in broad daylight, wondering why it was suddenly getting cold 8 minutes after it had actually disappeared.
We are always looking into the past when we look at the sky.
Always.
Okay, let's start to zoom in. We have a star, our sun, but we need a place to stand. Let's talk about planetary evolution, the why behind the rock we live on. How do we get from a swirling gas cloud to a solid planet?
It's a 3-stage process, according to the NCERT text. First, inside that spinning disk around the young star, gravity starts to pull gas together to form a core. A rotating disk of gas and dust develops around that core.
Okay, stage 1 is the core. What's stage 2?
Condensation. As the disk cools, the gas and dust start to turn into solid particles. And the text introduces a key term here: planetesimals.
Planetesimals, little planets.
Essentially, yes. These are small, rounded objects that are formed by a process called cohesion, where particles just gently stick together, but then it gets more violent.
This is where accretion comes back in.
This is where accretion really takes over. These planetesimals start colliding. They're smashing into each other, sticking together, and forming larger and larger bodies. It's like a cosmic demolition derby, but in reverse. Things are crashing to build up, not break down.
And stage 3 of this process?
Stage 3 is the final cleanup phase. These larger bodies, now with significant gravity, continue to accrete. They sweep up all the remaining debris in their orbits until you are left with just a few large, stable bodies, and those are the planets.
And our solar system finally formed about 4.6 billion years ago.
That's the current estimate, yes. We have 8 planets, 63 moons, though that number keeps changing with new discoveries, but we stick to the text for the exam, and then millions of asteroids, comets, and other debris.
And we have to mention poor Pluto.
We do. In August 2006, the International Astronomical Union had a meeting and officially reclassified Pluto. It's now known as a dwarf planet.
It just didn't make the cut. And it was demoted along with, wait, let me check my notes. Celestial object, 2003, UB313. What a catchy name.
They eventually gave it a proper name, Eris. But yes, Pluto is out of the main club. The main reason is it failed to meet the third criterion for being a planet. It hasn't cleared its orbital neighborhood of other objects.
Now, here is the question that I think is the most important, most fundamental part of this whole section. It's what I call the Great Divide. We have the inner planets, Mercury, Venus, Earth, Mars. They're all small and rocky, terrestrial. And then we have the outer planets, Jupiter, Saturn, Uranus, Neptune. They're enormous gas giants. Jovian. Why? Why are they so different?
This is a beautiful piece of deductive reasoning, and the NCERT lays it out so clearly. It gives 3 specific conditions. If you get a mains question on planetary formation, this is basically your body paragraph right here.
Okay, let's break them down one by one. Condition number 1, location and temperature.
It's simple physics, really. The terrestrial planets, like Earth, formed very close to the parent star, the Sun. And it was just too warm in that region.
Too warm for what?
Too warm for gases to condense into solid particles. They just stayed as gas. So only materials with very high melting points, like rock and metal, could solidify and form planets.
If you're close to the fire, you only get rock and metal. The gas just stays as vapor.
Exactly. But the Jovian planets were much farther away. It was very cold out there. So gases like hydrogen and helium could freeze and condense into solid ice particles, allowing them to be part of the planet-building process, leading to these massive gaseous bodies.
Okay, that makes sense. Condition number 2, the solar wind.
Right. This is a dynamic force we need to consider. The solar wind is a stream of charged particles constantly flowing out from the sun, and this wind was most intense near the sun.
And it acted like a cosmic leaf blower.
That's the perfect analogy. It literally blew off most of the gas and dust from the forming terrestrial planets. It stripped them of their primordial atmospheres.
But it wasn't strong enough to affect the outer planets.
By the time the solar wind reached Jupiter or Saturn, it had weakened considerably. So they were far enough out to be safe from this stripping effect, and they could hold on to their massive gas envelopes.
Okay, and that brings us to condition number 3, gravity.
At the end of the day, size matters. The terrestrial planets are much smaller. Their force of gravity is therefore lower. They just couldn't physically hold on to the light, escaping gases like hydrogen and helium.
But the Jovian planets.
The Jovian planets are massive. Jupiter's huge, so their gravity is incredibly strong, more than enough to hold on to even the lightest elements, which is why their atmospheres are primarily hydrogen and helium.
So to sum it up, Earth is a rock because it formed at a place that was too hot, too windy, and ultimately it was just too small to become a gas giant.
A perfect summary. Those are the 3 pillars of that explanation.
But Earth isn't totally alone in its orbit. We have a companion, a sidekick, the moon, and the story of how the moon got here is, well, it's pretty violent.
It is, but it wasn't always thought to be that way. The early theory, from 1838, came from Sir George Darwin. Yes, the son of the famous Charles Darwin. He suggested what's called the dumbbell theory.
Dumbbell theory. He thought Earth and the moon were once a single body.
That's right. He imagined a single, rapidly rotating body of molten rock. It spun so fast that it started to stretch out into a dumbbell shape, and then it just snapped. The smaller part broke off and became the moon.
And he even had an idea for where it came from, right? It's a specific spot on Earth.
He did. He argued that the massive depression that is now the Pacific Ocean is the scar left behind when the moon broke away.
It's such a cool visual, imagining the moon just popping out of the Pacific like a cork from a bottle.
But
modern science says no.
Modern science says no. The physics of the spin required doesn't really support it, and more importantly, the compositional data we have from moon rocks points in a different direction. The current, widely accepted theory is the giant impact, or as it's more excitingly known, the big splat.
I love that name, the big splat. It sounds like something from a comic book, a splat bubble.
It's very descriptive. The theory goes that about 4.44 billion years ago, very shortly after the Earth itself had formed, a body roughly the size of Mars, an object astronomers sometimes call Theia, crashed into the early Earth.
A Mars-sized body collision.
Yeah.
That is catastrophic. That's not a fender bender, that's a total planetary wreck.
It would have been an extinction-level event if there had been anything to extinguish. It was a glancing blow, but it blasted a huge chunk of the Earth's mantle and the impacting body into space.
And that debris didn't just fly off into the cosmos.
Nope. It went into orbit around the wounded Earth, and over time, through accretion again, it all clumped together to form our moon.
So the moon is essentially made of Earth stuff.
Largely, yes, a mix of Earth's mantle and the impacting object. And this explains why the moon's composition is so similar to Earth's mantle, and also why it has a very small iron core. It's our cosmic baby, born from a truly cataclysmic collision.
Okay, so we have a rocky Earth and we have a moon made from its debris. But the Earth back then wasn't the blue marble we see in photos. It was a barren, rocky, hot mess.
A literal hellscape. The Hadean aunt, named after Hades. It was volatile, primordial. It had a thin atmosphere of just hydrogen and helium that it couldn't even hold on to.
So how did we get from that molten, uniform ball of rock to this, the layered planet, the planet with a crust, a mantle, a core?
This brings us to probably the most important concept for understanding Earth's internal structure, differentiation. This is a high-priority keyword for your mains answers.
Unpack it for us. What is differentiation?
Think of a melting pot, or even a simple bottle of salad dressing. The early Earth was getting heated up from two sources: continued bombardment from space, like that moon impact, and from the inside by the decay of radioactive elements. It became semi-molten.
So it was basically a giant ball of liquidish rock.
Yes. And when you have a liquid mixture of different materials, what happens to the heavy stuff?
It sinks to the bottom, like when you let salad dressing sit. The dense vinegar sinks below the lighter oil.
Exactly. It's density separation on a planetary scale. The heavier materials present in the early Earth, mostly iron and nickel, sank down towards the center. That gave us our dense metallic core, which geologists call knife for knife.
And the lighter stuff floated.
The lighter materials, things like silica, aluminum, floated towards the surface. That cooled and solidified to give us the crust. And the material left in the middle, with medium density, became the mantle.
And the moon impact, the big splat, actually helped this process along.
It did. It added a tremendous amount of heat to the Earth, which further melted it and accelerated this process of differentiation into the distinct layers we know today: crust, mantle, outer core, and inner core.
And this layering is absolutely crucial because it's what sets up the entire system of plate tectonics.
It is the absolute prerequisite. Because Earth differentiated, we have a thin, rigid shell, the lithosphere, which is the crust, plus the uppermost mantle floating on a weaker, semi-molten layer called the asthenosphere.
And I want to jump to a 2025 GS1 question here because this is a perfect link. Question 16 asks, discuss how the changes in shape and sizes of continents and ocean basins of the planet take place due to tectonic movements of the crustal masses.
This is a direct application of the concept of differentiation. Because we have that internal structure, we have an engine. The heat from the core, that residual heat from formation and ongoing radioactive decay, tries to escape. It sets up huge, slow-moving convection cells in the mantle.
Like the circulation in a pot of boiling soup.
Exactly. Hot, less dense material rises, spreads out along the bottom of the lithosphere, drags the crustal plates with it, then it cools, becomes denser, and sinks back down. This dragging motion is what moves the plates. It tears continents apart at rift valleys, it crashes them together to form mountains, and it opens up new ocean basins.
So without that initial differentiation, this dynamic engine wouldn't exist. Earth would be a geologically dead, solid rock, probably more like Mars or Mercury.
That's right. So when you answer that 2025 question, you don't just start by talking about plates moving. You can add a line or two about why they are able to move, because of the planet's layered interior, which was formed through the process of differentiation.
That adds the kind of depth and root cause analysis that examiners absolutely love. It shows you understand the entire system.
It connects the origin story to the present-day geography.
Okay, so we have the rock and we have the internal engine, but we need air to breathe and water to drink. Segment 7, evolution of atmosphere and hydrosphere.
The evolution of our atmosphere happened in 3 distinct stages, according to the text. Stage 1 is the loss of the primordial atmosphere.
That initial flimsy layer of hydrogen and helium.
Yeah.
Is the solar wind the culprit again?
The solar wind is the culprit again. It was just too strong, and the Earth's gravity was too weak. It stripped away that first atmosphere. And this happened to all the terrestrial planets. So the first atmosphere was basically blown away into space.
Okay, so we're left with a bare rock. Stage 2, the hot interior strikes back.
This is the process of degassing, another critical term. As the Earth's interior cooled and began to solidify, the gases and water vapor that were trapped inside the molten rock were released.
Like opening a can of soda that's been shaken up.
A very similar kind of pressure release, yes. This happened on a massive scale through volcanic eruptions. Volcanoes just poured out gases from the Earth's interior. And that early atmosphere consisted of water vapor, nitrogen, carbon dioxide, methane, ammonia.
And it's important to note what's missing from that list.
What's crucially missing is free oxygen. There was very, very little free oxygen in that second atmosphere. If you stepped out of a time machine into that world, you would suffocate instantly.
So where did our oceans come from, all that water?
It came from the water vapor. That was the most abundant gas being pumped out by volcanoes. As the Earth continued to cool from the outside, that water vapor in the atmosphere began to condense into clouds. And then it started to rain.
It didn't just rain for an afternoon.
It rained for thousands, perhaps millions of years. Just imagine a continuous planet-wide rainstorm that lasts for millennia. And as it rained, the CO2 in the atmosphere dissolved into the rainwater, which made it slightly acidic. This actually helped to cool the surface further, causing even more condensation.
And all that rainwater collected in the low-lying areas, the depressions.
The basins, and that's how the oceans were formed. The text says the oceans formed within 500 million years of the Earth's formation. So they are incredibly old, roughly 4 billion years old.
Yes.
And here's the beautiful plot twist in the story. Life began in those oxygen-poor oceans around 3.8 billion years ago. But for a very long time, it was just anaerobic life that didn't need oxygen to survive.
And that brings us to stage 3, modification by life. This is where the planet gets a serious makeover, the oxygen flood.
This is where biology takes over geology. Photosynthesis evolved. The text places it around 2.5 to 3 billion years ago, with organisms like cyanobacteria or blue-green algae. They started taking in carbon dioxide and, as a waste product, releasing oxygen.
But that oxygen didn't immediately go into the air, did it?
No, not at first. For hundreds of millions of years, the oceans acted like a giant sponge. The oxygen reacted with the dissolved iron in the water, creating rust that settled on the ocean floor, forming what we call banded iron formations. The oceans had to become completely saturated with oxygen first.
And only after the oceans were full could the oxygen start leaking into the atmosphere.
Only then. And that great oxidation event happened around 2 billion years ago. Oxygen finally flooded the atmosphere.
This is such a profound concept. Life didn't just adapt to the environment it found itself in. Life fundamentally created the environment we have today. We are literally breathing the waste product of ancient bacteria.
We absolutely are. The biosphere modified the atmosphere. It's a perfect example of a reciprocal relationship, a feedback loop.
Speaking of life, let's quickly hit the geological timescale. The cheat sheet. I know this table in the insert scares a lot of students. It's just this massive list of eons, eras, and periods with strange names and big numbers.
It shouldn't scare you. You don't need to memorize every single detail. You just need to understand the flow of the story. It's the story of us.
So let's just run through the absolute highlights.
Okay, start with the eons. You have the Hadean, which we talked about, named after Hades, the hellish beginning. Then the Archean, which means ancient or beginning. This is when you get the first signs of life, the blue-green algae unicellular organisms. Then the Proterozoic, which means earlier life. You start to get more complex, soft-bodied things like arthropods.
Okay, then we get into the Phanerozoic eon, which is divided into eras. The first is the Paleozoic era, the era of old life.
And within that, the most important period for geography is probably the Carboniferous period. This is important because it's when the first reptiles appeared. But more importantly for us, this is when the great coal beds were formed. The vast swampy forests that died got buried and became the energy source that powered the Industrial Revolution. When you burn coal, you are burning the Carboniferous period.
Then comes the Mesozoic era, the age of middle life.
The fun one. This is the Jurassic, the Cretaceous, this is the age of the dinosaurs, everything is big. And then at the end of the Cretaceous, 65 million years ago, a massive extinction event. The asteroid hits.
And that ushers in the final era, the Cenozoic, the age of new life.
And within that, we live in the Holocene epoch. That's the last 10,000 years since the end of the last major ice age. This is the time of modern man, Homo sapiens.
It really puts our existence in perspective. The entire history of human civilization is a tiny, tiny blip on this timeline. If the Earth's history were a 24-hour clock, humans showed up in the last second.
A very noisy and impactful blip.
Laughs, that's true. Now, we've covered the origin and the evolution, but this is simplified UPSC. We need to really hammer home how to connect these dots. We've already touched on the Higgs boson and the tectonic movements question. Let's look at a few more PYQs to show how this chapter feeds directly into the exam.
Let's look at a classic question. 2014 GS1, question 17. Why are the world's fold mountain systems located along the margins of continents? Bring out the association between the global distribution of fold mountains and earthquakes and volcanoes.
Okay, this is a core physical geography question. How does Chapter 2, the origin story, help us answer it?
Chapter 2 gives you the fundamental mechanism. Because of differentiation, we know we have a hot interior fueled by radioactive decay. We know this heat drives convection in the semi-molten mantle. We know these convection currents move the rigid plates of the lithosphere. Fold mountains, like the Himalayas or the Andes, are the direct result of these plates colliding.
And they collide at the margins of continents.
Often, yes. An oceanic plate colliding with a continental plate, or two continental plates colliding. This collision doesn't just fold the rock to create mountains. The immense friction generates earthquakes, and the subducting plate melts, creating magma, which rises to form volcanoes.
So the answer isn't just because plates hit each other. A top-tier answer would root it in the endogenic forces that are derived from the Earth's primordial heat.
Exactly. The residual heat and radioactive decay mentioned in Chapter 2 are the ultimate engine driving the formation of the Himalayas today.
What about the Ring of Fire? That came up in 2020 GS1, question 4. Discuss the geophysical characteristics of Circum-Pacific Zone.
It's the same underlying principle, just applied to a specific region. The Circum-Pacific Zone, or Ring of Fire, is a massive chain of volcanoes and earthquake sites around the Pacific Ocean. Why is it there? Because the Pacific Plate is interacting with numerous other plates along its margins.
Subduction zones.
Massive subduction zones. And you can link this back to the concepts in the next few chapters, like seafloor spreading, but the engine is the same one we established here. The geophysical characteristics, trenches, volcanic arcs, high seismic activity, are all surface expressions of the heat engine born during Earth's formation.
Okay, one more. This one is about resources. 2025 GS1, question 14. Give a geographical explanation of the distribution of offshore oil reserves.
This connects beautifully back to segment 7 of our discussion.
The evolution of the atmosphere and hydrosphere.
Precisely. Remember how the oceans formed? Rainwater collected in depressions. For billions of years, marine life, plankton, algae thrived in these oceans. When these organisms died, they sank to the bottom of these basins.
And they got buried.
They got buried by layers and layers of sediment, washed off the continents. Without oxygen at the bottom, they didn't fully decay. The heat from the Earth's interior and the immense pressure from the overlying sediments cooked this organic matter over millions of years, transforming it into oil and natural gas.
So, offshore oil reserves are essentially ancient marine graveyards located in the sedimentary basins that were formed by the early Earth's cooling and raining process.
That's the perfect geographical explanation. You find oil in the thick sedimentary layers on the continental shelves, the shallow margins of those ancient ocean basins. Understanding the biological history, which started in the oceans, and the geological history, the formation of those basins, gives you the complete answer.
It really does connect everything. The biology, the geology, the chemistry, it all comes together.
That is the absolute beauty of physical geography. It is a synthesis science.
Wow. We have covered a lot of ground and a lot of space today. It's been a journey.
Let's just do a super quick recap of that journey.
We started with the Big Bang, 13.7 billion years ago, the singularity, the expansion, the cool.
And we moved to star formation inside those giant gas clouds, the nebulas.
From there, we got planet formation, driven by the process of accretion, the planetesimals smashing together.
We covered the Great Divide, why the inner planets are rocky, too hot and windy, and why the outer planets are gas giants.
We witnessed the big splat, the giant impact that gave us our moon.
We saw how the Earth separated into layers, crust, mantle, core through differentiation.
We talked about degassing from volcanoes giving us our second atmosphere, and millennia of rain filling the oceans.
And finally, we saw how the spark of life, through photosynthesis, oxygenated the entire planet and made our existence possible.
And throughout this entire story, we've seen how this deep history answers very specific questions about mountains, earthquakes, and oil reserves that you will face in the UPSC Mains.
It's a complete, interconnected narrative from the cosmos to your exam paper.
Before we sign off, I want to leave you with one final provocative thought. The insert text in a later chapter talks about the balance between endogenic versus exogenic forces. The internal forces from the Earth's heat build the land up, and the external forces like wind and water wear it down. It's a natural balance.
But the text also says something profound, which you can use in your essays. It says, humans are now a major geomorphic agent.
Think about that for a second. We aren't just living on the surface anymore. We are actively shaping it. We are mining, building dams, moving mountains, changing river courses, and warming the entire atmosphere. We are disrupting a delicate balance that took 4.6 billion years to stabilize.
The text gives a warning. It says, use we must, but must also leave it potential enough to sustain life.
So the question to leave you with is this. Are we the new asteroid, a force of extinction? Or are we like those early photosynthesizing bacteria, a force that will create a whole new kind of planet, a new epoch? That's something for you to mull over.
Indeed. A powerful thought to end on.
All right, that officially brings us to the end of this deep dive by Simplified UPSC by PPP.
We hope your brain feels a little bigger and a little more connected to the cosmos than it did an hour ago.
Please, if you've made it this far, subscribe if you haven't already. It's just one click for you, but it means the world to us.
And again, a humble request. If you're capable and find this valuable, please consider supporting us on Patreon. It helps us keep the lights on, keep the research going, and keep this content coming your way.
A huge final shout out to our supporters. You guys are the real MVPs, the engine of this channel.
And don't forget to like and leave a comment. We'd love to hear your favorite theory. Are you Team Nebular or Team Big Splat?
And one last reminder. The free notes and practice quiz IQs are on the public Telegram. But for that library experience, with the premium notes, extra PYQs, and those crucial model mains answers, send a DM to the public channel to join the private library.
It is absolutely worth it.
Until next time, keep looking up and keep digging deep.
Goodbye, and good luck with your preparation.